Chapter 6, Transformations. Section 6.1, What, Why, and How of Data Transformations. Section 6.1.1, What are data transformations? Data transformation involves the application of a mathematical operation or a sequence of operations to your data. As a simple example, consider the following dataset and its transformed version. We have dataset X equals 1, 3, 4, 6, 7, and dataset X star is 0, 2, 3, 5, 6. The transformation applied to get from X to X star is subtracting 1 from all values. Now, I never claimed that this was an interesting or complex transformation, but it is a valid data transformation. Many data transformations are simple and can be expressed in one or a few mathematical or algorithmic expressions. To be sure, simplicity is not intrinsic to data transformations. There are incredibly sophisticated transformations that are described by mathematically dense technical documentation and require hours or even days for a high-powered computer to implement. But the complicated transformations tend to be discipline and data specific, while the relatively simple transformations tend to be generally useful in many applications. Section 6.1.2, Why transform data? There are several reasons to transform data, but they all stem from the same underlying motivation: to fix, or at least lessen, a problem with the data. Here is a non-exhaustive list of data issues that transformations can ameliorate. Point 1. Multiple data sets should be compared, but they are in different scales, for example, distance and mass. Transformations such as z-scoring and min-max scaling can put the data into the same numerical range, thereby enabling direct comparison. Point 2. The data have a non-normal distribution, but the statistical analyses require normally distributed data. Various transformations, including log or square root or Fisher Z, can mutate a non-Gaussian to a Gaussian distribution. Point 3. Related to the previous point, some analyses require data to be within certain numerical ranges. For example, some image processing techniques expect data in the range of 0 to 1, whereas raw image data are integers between 0 and 255. Point 4. There are extreme values in the data that negatively impact the results, and their impact can be minimized or obliterated through a transformation. Log, square root, and tide rank transforms can be useful in these cases. Point 5. Statistical parameters reported in the scale of the data may be difficult to interpret, and transformations may facilitate interpretation. This situation arises in regression analysis, which you'll learn about in Chapter 15. Z-scoring is a common transformation that anyone with statistical training, including you after reading this chapter, is comfortable with. Final point. Sometimes data are transformed for non-statistical purposes, for example, to facilitate data storage or transfer. Section 6.1.3, How to transform data. As I wrote above, transforming data involves applying some mathematical operation or algorithm to your data. But that's an abstract statement, so below I'm going to make this a little bit more concrete. You can call a Python or R function. Python libraries like NumPy and SciPy.stats and functions in base R and libraries such as caret include functions to apply most of the commonly used data transformations that you will need. When using library-provided functions, just be mindful that functions vary in how intuitively they can be implemented and in the readability of the documentation. You can download a function that someone wrote. The internet is ripe with code that people post, for example, on GitHub or personal website. However, please use caution when using code written by a non-professional developer. There are no guarantees that the code is accurate simply because it's on GitHub. So check the code carefully before using it and confirm its accuracy, for example, using simulated data. You can write code yourself. There are many exercises in this book that guide you in writing transformations, analyses, and algorithms from scratch. In many cases, these algorithms are already implemented in libraries like NumPy or SciPy or in R. Writing custom code for data transformations has strong educational value and also practical advantages in terms of usability or speed. And you also may need data transformations that are not packaged with any software libraries. Regardless of where you get the code, be mindful that not all transformations are appropriate for all data sets. And also be aware that most transformations have assumptions about the data type and valid numerical ranges. For example, you cannot take the square root of negative numbers. Some assumptions may not be obvious unless you look at the equations or take the time to understand the methods, for example, by reading this chapter. Running some code to transform your data is easy. Knowing when to use which transformation and how to interpret the results, well, that requires statistical training and critical thinking. Never apply transformations to your data that you don't understand or cannot justify. Section 6.1.4, what kinds of transformations are there? There is no widely agreed upon taxonomy of data transformations, and I am not a fan of artificially imposed taxonomies because, they often misrepresent categorical distinctions and relations. But it can be useful to think about commonalities and differences in groups of data transformations. There are linear and nonlinear transformations, lossy and lossless transformations. So here, lossy means that information is lost after the transform is applied. There are iterative and non-iterative algorithms, where iterative means that steps of an algorithm are repeated until some criterion is reached. The goal of this chapter is to equip you with a comprehensive understanding of various transformations, their characteristics, and their implications. I hope that by the end of this chapter, you will have the tools that you need to apply data transformations, and that by the end of this book, you will have all the knowledge you need to make informed decisions about when and how to transform your data in practice. Section 6.2, Z-score standardization. Z-scoring is probably the most ubiquitous and most important transformation in all of statistics. Footnote: depending on your country of origin or residence, you might pronounce this as Z-score or Z-score. I believe some famous statistician once said that we should judge a data scientist by their skill in transforming data and not by their pronunciation of a letter, or something like that. Back to the text. Let's start with a problem that Z-scoring will solve. Imagine that we want to know whether someone weighs a lot or a little given their height. Now, the problem with this comparison is that the units are completely different. Height is measured in centimeters, or inches, or light years. Let's stick with centimeters for convenience. And weight is measured in kilograms. Now, these are not directly comparable metrics. It doesn't make sense to say, for example, that 177 centimeters is taller than 70 kilograms, whatever that means. A solution to this problem is to shift our mindset from absolute measurements to relative measurements. So on the one hand, 177 centimeters is a meaningful and interpretable measurement, but we can also consider that in a population of Armenian adult males, 177 centimeters is 5.5 centimeters taller than average, while 70 kilograms is 4.6 kilograms lighter than average. So, assuming that our individual is an Armenian adult male, we can say that he is taller than average while weighing less than average. Figure 6.1 illustrates the concept. Figure 6.1 illustrates an example of the benefit of using Z normalization to compare data that have qualitatively different units. These are all fake data displayed in this figure. So we have two rows, a top row and a bottom row, and there are 3 subpanels within each row, so 6 subpanels in total. The top left panel shows an empty plot with a vertical dashed line, and the x-axis ranges from around 135 to 220 centimeters. The dashed line is at approximately 177 centimeters. The next panel in the middle shows a histogram of raw heights. This shows a histogram of height data. It's roughly Gaussian, and we see that the vertical dashed line at 177 is a little bit above the average of the distribution. And then we have in the third panel a histogram of z-scored heights. Now we have on the x-axis, the numerical values go from around minus 2.5 to plus 2.5 with 0 in the middle. This is a histogram that looks qualitatively very similar to the histogram in the middle panel, but the x-axis range and scale is different. Okay, so I've just described the top panel. The bottom panel is this similar, except this shows data for weights instead of heights. Here we see that the vertical dashed line at 70 kilograms is a little bit below the mean of this distribution. Back to the text. Panels A, 1, and 2, so these are the leftmost panels on the top and bottom row, show the height and weight data of one individual. The scales are completely different, so we cannot compare them. Panels B, 1 and 2, this would be the middle panels in the top and bottom row, show the same individual's data plotted on top of a histogram of sample data collected from other adult male Armenians. The scales are still incomparable, but you can see that the individual's data can be conceptualized as a certain value relative to the distribution. Panels C, 1 and 2, so these are the two subplots on the right, top and bottom rows, show the data normalized to z-scores. The individual data are now recoded to the number of standard deviations away from the mean of the distribution. For example, it looks like the height of this individual is around 1.5 standard deviations above the mean, while the weight is around 1 standard deviation below the mean. Now, the benefit of this reinterpretation to relative units is that we can now directly compare height and weight. This individual is tall, yet relatively light for the population of Armenian males. Section 6.2.1, Z-score math. The math of Z-scoring is simple, but there are hidden assumptions behind it which can lead to interpretational difficulties when data violate those assumptions. In the subsection entitled Hard and Soft Assumptions, I will describe a few limitations and potential awkward features of Z-scoring. Before then, I would like you to think of some potential issues when applying and interpreting Z-scoring. Anyway, Z-scoring data involves 2 simple transformations. Step 1, shift the data by its mean such that the average of the transformed data is x bar equals 0. This is called mean centering or demeaning. It is done by subtracting the mean of the feature from each data point. Step 2, scale the data by its standard deviation so that the standard deviation of the transformed data is s equals 1. This is done by dividing each data point by the standard deviation of the data set. I hope that explanation is clear. Here's the formula. So equation 6.1 reads z sub I, so the ith element in the z transform data z, equals a fraction. In the numerator, we have x sub I minus x bar, and in the denominator, we have s. This transforms each data point I. Notice that the mean and standard deviation are from the entire data set. If the population characteristics are known or can be assumed, you would use mu in place of x bar and sigma in place of s. Let's work through an example. So we have a data set x equals 1, 4, minus 5, 2, 1. X bar, the average of x, equals 0.6, and s equals approximately 3.36. And this gives us x sub z, so the z-scored transformation of dataset x, equals 0.12, 1.01, minus 1.66, 0.41, and 0.12. I used the approximately equal sign because I truncated the numerical values. Z-transform numbers are rarely nice to work out like integers. Indeed, the Z-transform is a simple algorithm, yet definitely not something you would want to implement by hand. And full disclosure, I used Python to get the numbers that I just read off. So the table below shows the mean and standard deviation of the original and the Z-transformed data sets. So here we have a table with the rows corresponding to the mean and the standard deviation. The columns are the original data set and the Z-transformed data set. The mean of the original and Z-transformed data are respectively 0.6 and 0. The standard deviations are 3.36 and 1.00. The mean and standard deviation of a Z-scored dataset are always 0 and 1 by definition. And by the way, the variance of Z-transformed data is also 1 because 1 squared equals 1. Now, Z-transforming does not alter the shape of the distribution and therefore does not change the skew or kurtosis. I'll show examples of this later, but I hope that's clear from the formula. Section 6.2.2, Interpretation. The interpretation of the Z-score is that each data point is interpreted as a normalized distance to the center of a distribution. More specifically, the numerical value of each data point is the number of standard deviations that point is away from the mean, where the standard deviation and the mean correspond to some distribution. And usually it's the distribution from which the data point was drawn. Now, the reason for this interpretation is that the units of Z-score are standard deviations. Notice what happens with the units in equation 6.1. The numerator and the denominator have the same units of the data, for example, feet or seconds or grams or counts. So those units cancel in the division, leaving us with a unitless metric. That is convenient because it allows us to compare data values from different measurements, such as height and weight. This is also a reason for scaling by standard deviation instead of variance. Variance scaling would put the Z-score into units of the reciprocal of the data. For example, data in feet would have Z-score in units of 1 over feet if we used variance instead of standard deviation in the formula. Importantly, the Z-transform shifts and stretches the data, but does not change the shape of the distribution. So that is, the units of the data change, but their relative values do not. We shift the distribution on the x-axis and we stretch the distribution on the y-axis, but there is no warping or difference in how the transformation impacts some data values compared to others. This can be contrasted with the nonlinear transformations that you'll learn about later in this chapter. This paragraph references figure 6.2, which shows data before on the x-axis and after on the y-axis Z-scoring. The transformation does not affect the relative values within the data set, evidenced by the perfect linear relationship between the pre- and post-transformed data. So the figure illustrates a scatter plot where the x-axis ranges from maybe around 100 to 400, and the y-axis ranges from -2 to around 2. And what you see is that all of the individual data points lie perfectly on the diagonal line of unity. So there would be a perfect relationship, a perfect linear correlation between the original and the Z-transformed data. Section 6.2.3, Hard and Soft Assumptions. Now, by quote-unquote hard and quote-unquote soft assumptions, I refer respectively to mathematical issues and interpretational issues. The main hard assumption of z-scoring is that the standard deviation is non-zero. If sigma equals 0, then the transformation involves dividing by 0. So when would this standard deviation be 0? Well, when there is no variability in the data. And this happens when all data points have exactly the same numerical value. And if all of your data have exactly the same value, then there's probably a mistake somewhere. All right, now let's talk about the soft assumptions. These are features of your data that can make the z-scores easier to interpret, but violations of these assumptions do not invalidate the math. The key soft assumption is that the mean and standard deviation are useful descriptive statistics of the data. Now, this is definitely the case for any distribution that is Gaussian-like. That is, the data values are more likely towards the middle of the distribution and are roughly symmetric around the mean. Let's consider a counter example. Figure 6.3 shows data with an exponential distribution comprising positive valued data. Now, technically, we can compute the mean and standard deviation, but the mean does not really reflect the central tendency of the data. That is, the expected value of a randomly selected data point is not the mean. So that makes the z values awkward to interpret. For example, in a Gaussian distribution, z-scores farther away from 0 correspond to more extreme values that are less likely to occur. But in an exponential distribution, a data point with z equals -1 is actually more likely to be randomly selected than a data value corresponding to the mean, or to z equals +1. Another awkward feature in this example is negative z-scores coming from a dataset with only positive values. So this paragraph references figure 6.3, which shows a distribution of data before in the top panel and after in the bottom panel z transformation. The data are roughly power law distributed, so we see that small values close to 10 are much more likely to occur, and as the data value, so the x-axis, increases, the count of the histogram decreases and it drops precipitously. The raw data in panel A on top ranges from 10 to around 80, whereas the histogram on the bottom it shows the z-transform data. These numerical values on the x-axis range from -1 to around +5. We also see a vertical dashed line corresponding to the mean, which is at around 20, a value of 20 in the raw data, and of course a value of 0 in the z-transformed data. Back to the text. Is violating this soft assumption fatally problematic? No, it isn't. For example, in the next chapter, you will learn about using z-scores to identify outliers in data. In this case, we use z-scores to facilitate data cleaning, but do not interpret the z-scores or use them in statistical analyses. The main point is to be mindful of the data distribution when interpreting z-scores. There's a margin note here which reads, "There is an important theme here that permeates this book, and indeed all of statistics, which is that statistics is not simply about applying some algorithm to data. You need to understand what the algorithms mean, when to use them, and how to use them." Back to the text. Finally, because z-scoring involves comparing a data point with a distribution, the z values are easily interpretable only if each data point is qualitatively similar to the population from which the distribution is sampled. For example, at the outset of this section, I discussed the height and weight of an individual relative to the population of an Armenian adult males. But what if our individual is a 10-year-old girl from Peru? Well, her height and weight will be several standard deviations below that population, although she may be a perfectly average 10-year-old Peruvian. Again, there's nothing wrong with the math in this case, but the interpretation is confusing and misleading. On the other hand, there are cases where defining the mean and standard deviation based on different data makes sense. This is done, for example, in time series analysis, where data points in some time range, for example, the present, are computed relative to the distribution from a different time range, for example, in the past. Another example is with growth curves in children. When you were 5 years old and your pediatrician compared your height and weight to normative growth charts, the means and standard deviations in those charts were computed from a group of children that did not include you. Section 6.2.4, the modified Z-score method. If your data distribution is strongly non-Gaussian, you can consider using the modified Z-score. Note, for the rest of this section, I will refer to the regular Z-score method to indicate the one based on mean and standard deviation. Quote-unquote regular is not the official name, but it helps to contrast it with the modified Z method. For the rest of this book and the rest of your adventures in statistics, Z-scoring will always refer to the mean standard deviation variety. The modified Z-score method is conceptually similar to the regular Z-score method, but does not rely on descriptive statistics that are easily interpretable only for Gaussian-like data. In particular, instead of subtracting the mean and dividing by the standard deviation, the modified Z-score involves subtracting the median and dividing by the median absolute difference. But the concept is the same. Subtract a measure of central tendency from each data point and divide by a measure of dispersion. Equation 6.6 shows the formula. Equation 6.6 reads m sub I equals a fraction where the numerator is x sub I minus x tilde, and the denominator reads 1.4826 times MAD. The next equation, equation 6.7, shows that x tilde equals the median of x, dataset x, and equation 6.8 defines MAD, or MAD, to be the median of the absolute values of the differences between x sub I minus x tilde, or the median of dataset x. Let's start with equation 6.6. The numerator shows that each data point, I, is median-centered. So this you can compare with mean centering in Z-scoring. The denominator term is MAD, M-A-D. This stands for median absolute difference and is the median-based alternative to standard deviation. I'd like to first explain the median absolute difference before discussing the curious normalization constant of 1.4826. To understand the formula for the MAD, that is equation 6.8, recall or refer back to the standard deviation formula that was equation 4.9 on page 105. Standard deviation is calculated as the square root of the average squared distances from each data point to the data mean. The MAD, M-A-D, is calculated as the median of the distances from each data point to the data median. As you know, the mean and median are nearly the same for a symmetric distribution, which signifies that the standard deviation and the MAD would differ by squaring the distances. So the square root function shrinks down the impact of the squaring to some extent, but the upshot is that the standard deviation will generally be larger than the MAD. So a larger denominator produces a smaller fraction, hence the regular Z values will be smaller than the modified Z values. To help compensate for this difference in magnitude, the MAD is scaled up by a constant factor in the formula for the modified Z-score. This increase effectively shrinks the m sub I values, making them closer to the regular Z values for a normal distribution. Exercise 7 will guide you through an experiment that will help you develop intuition for this relationship. But why scale by 1.4826? Where does that number come from? It actually corresponds to the third quartile of a normal distribution. In fact, that constant is more formally written as phi of 3/4, and 1.4826 is an approximation of that quartile value. You will have a deeper understanding of what phi signifies in Chapter 8. Figure 6.4 shows a comparison of the regular and modified z-score transformation on a dataset. You can see that the two methods produce overall similar histograms that differ only in some stretching, with the modified Z being slightly wider. Figure 6.4c further highlights this difference. So values along the dashed line of unity would mean that the two transforms were identical. Instead, the modified Z values stretch below and above the line of unity towards the edges of the distribution. Now, because the mean and standard deviation are differentially impacted by the shape of the distribution compared to the median and the MAD, the shift off of the unity line here is an illustration of how the two transformations can relate to each other. The precise relationship will depend on the characteristics of the data. So this paragraph refers to figure 6.4. Figure 6.4 shows a comparison of regular and modified z-scoring of non-normally distributed data. So we have three panels A, B, and C, arranged in a row. In panel A on the left, we see a histogram. This is the original data distribution. It is a bimodal distribution of data with one large peak at somewhere around 6 or 7 and a smaller peak at around 11. Panel B shows the z-score distributions for the regular in a solid line and the modified in a dashed line. Now, the histograms of the z-scored data, of course, look very, very similar to the histograms of the original data, but the modified z-score is a little bit stretched. It spans a slightly larger range on the x-axis compared to the regular z-score data. And then we have panel C on the right that shows the regular by the modified z-score. There is a gray dashed line corresponding to the line of unity, and then there are black circles drawn in for each data point. Now, all these circles lie perfectly on a line, but that line does not exactly correspond to the line of unity. So this indicates that although the regular and modified z-score values are super tightly related to each other, they're perfectly related to each other, but they are not on the line of unity. So there's some differences between them. Back to the text. But there is a more important point that figure 6.4 highlights, which is that the regular and modified z-scores are generally similar to each other. That is to say, it is unlikely that you would come to a qualitatively different conclusion about the data using one method or the other. Now, that should not be surprising, considering that the two methods are conceptually identical. You shift by central tendency and scale by dispersion. So, when should you use the modified Z method? Either for non-Gaussian distributed data or for data that have large outliers. The latter is because the median is less influenced by outliers compared to the mean, and for the same reason, the MAD is less influenced by outliers compared to the standard deviation. This explains the difference in stretching in figure 6.4. Now, maybe you are thinking that you should always use the modified Z. There is merit to that argument. After all, the two methods are similar, and the modified Z is more robust to non-normal distributions and to outliers. However, the mean and standard deviation have useful mathematical properties such as a well-defined derivative, relation to a chain of statistical moments, easier interpretation as standard deviation units, and so on. Therefore, the regular z-score method should be used whenever possible, and the modified z-score should be used only when necessary. In practice, modified Z is mostly used to identify outliers during data cleaning, whereas the regular Z method is used to transform data into standard deviation units to facilitate model fitting and interpretation. Section 6.3, Min-Max Normalization. Min-max normalization involves rescaling the data to have minimum and maximum values that you specify. Typically, the new scale is 0 to 1, but it might be -1 to +1, or 0 to 2 pi, or anything else. I will first show you how to normalize any data set to a range of 0 to 1, and then expand that to any other range. Equation 6.9 reads x tilde sub I equals a fraction with the numerator being x sub I minus the minimum of x, and the denominator is the maximum of x minus the minimum of x. Back to the text. Min x and max x are the smallest and largest values, smallest meaning most negative, not closest to 0. The denominator is the total range of the data. So think about it this way. The numerator shifts the data so that the new smallest value is 0. Then imagine the denominator as a second transformation step with the minimum of x equals 0. Now we are dividing by the maximum value, which scales the data to a max value of 1. Figure 6.5 shows an example of a dataset that is min-max scaled. Panel C shows that the relationships between the data values are unchanged by this transformation. Figure 6.5 shows 3 scatter plots arranged from left to right, panels A, B, and C. Panel A shows a scatter plot of the original data, and here we have the data scale ranging from around 300 to around 900. Panel B shows the scaled data. The values here range from 0 to 1, and the y-axis is labeled Unity Normed Data Scale. Panel C shows a scatter plot of the original data values on the x-axis by the scaled data values on the y-axis. All of the data points in panel C lie perfectly on a diagonal line, indicating that there is a perfect relationship between the original data and the normalized or scaled data values. Back to the text. Equation 6.9 puts the data into a unit range. If you want the data in any other range, you can shift x tilde by any specified lower and upper bounds. And those are respectively A for the lower bound and B for the upper bound in equation 610 below. So equation 610 reads x star equals A plus B minus A in parentheses, x tilde. I hope equation 610 looks a bit familiar. If not, please refer back to equation 5.5 about transforming a standard uniform distribution into a dataset with any lower and upper bounds. As a linear transform, min-max scaling does not change the shape of the distribution, nor is it applicable only to uniformly distributed data. But uniform distributions and min-max scaling both have lower and upper bounds as key descriptive characteristics. Now, it turns out that you can combine equations 6.9 and 610 into a single equation, and discovering that equation is the hors d'oeuvre of exercise 1. Section 6.3.1, Interpretation. Just like with z-scoring, min-max scaling does not change the shape of the data distribution, nor does it affect the relative distances between values within the dataset. Indeed, it merely shifts and scales the data. It is often used in image processing to get pixel intensity values in the range of 0 to 1. It's also used in signal processing to scale a filter such that the numerical values reflect the gain or weighting characteristics of the filter. Figure 6.6 shows an example of data with values ranging from below -40 to over 20. The min-max scale distribution is bound by 0 and 1. So figure 6.6 shows two histograms in panel A on top, panel B on the bottom. Panel A is before and panel B is after min-max scaling. And the point that this pair of histograms is conveying is that the x-axis values are changed. Those are different between the two histograms, but the relative heights of the bars are exactly the same before and after this transformation. Section 6.4, Z-scoring versus min-max scaling. When should you Z-score and when should you min-max scale? In some cases, it doesn't matter if the goal is simply to restrict the numerical range of the data, for example, to facilitate comparison across measurements or to scale data in a machine learning model, then both methods could be equally appropriate. But there are some situations where one method would be preferred over the other. Z-scoring, for example, produces data with a known mean and standard deviation, whereas min-max scaling does not prescribe the descriptive statistical characteristics except for the lower and upper limits. For the same reason, the units of Z-scored data, standard deviations, are interpretable and universal. In contrast, the units of min-max scale data are arbitrary values not intrinsically related to the shape, moments, or other characteristics of the data distribution. Min-max scaling is most appropriate for data that are roughly uniformly distributed. That is, the data distribution does not have long tails. The reason is that a small number of extreme data values can squeeze the effective numerical range of the bulk of the data. For example, imagine a data set of normally distributed numbers with high kurtosis. After min-max scaling, it is possible that most of the data points will have values close to 0.5. And if this numerical squeezing becomes extreme, it could cause computer precision errors. Min-max scaling is mostly used when a particular analysis expects data in a restricted range. This is most often seen in machine learning classification algorithms like artificial neural networks. Nomenclature. In the machine learning literature, a distinction is made between normalization and standardization, with normalization referring to min-max scaling and standardization referring to Z-scoring. But don't be so strict with those terms. They are used interchangeably. For example, normalizing can be interpreted as transforming the data to having characteristics of a normal distribution, which fits the definition of standardization. Indeed, I had not encountered this terminological distinction until relatively recently, that is, many years after studying statistics in university. So indeed, this distinction between standardization and normalization is not codified into the statistics corpus, and you will often encounter the terms Z-normalization or Z-score normalization. Section 6.5, percent change. I'm sure you've heard of percent change. It is commonly used in shopping sales and public opinion polls, which are hallmarks of modern society. Percent change is used to quantify a change in a variable. This change requires two measurements, the change from something to something else. Now, the something can reflect a change over time, for example, before versus after a medical treatment, a change between different analysis methods, for example, the change in the data average after removing corrupted data, or the change in the cost of a product or service due to sales or inflation. The formula for percent change is simple and illustrated in equation 6.11. Equation 6.11 states that the percent change is equal to 100 times a fraction where the numerator is ref minus nu and the denominator is ref. Ref stands for the reference value, and multiplying by 100 gives the result as a percent, as in per 100. Because percent change is a relative transformation, the result will depend on the reference value. I'm pretty sure that shopping stores use this trick. Increase the base price and then increase the sales percentage, leaving the product with the same price that now seems more attractive because of the steep discount. Percent change is generally used only when 2 data points at a time are considered. This can be contrasted with the Z transformation. It wouldn't make sense to compute the Z-score on only 2 data points. An advantage of percent change is that it removes the original measurement scale of the data, which facilitates comparing data that have different scales or different measurements. Percent change is valid for numerical data when the reference value is non-zero. Reference values that are technically non-zero but very small might produce numerical inaccuracies or computer rounding errors. Percent change is used for positive value data like prices or weight or disease severity and so on. Now, the issue is that negative values can be difficult to interpret. For example, the percent change from 5 to 4 is a sensible and intuitive minus 20%. But the percent change from minus 5 to plus 4 is minus 180%. Many people would find it confusing that an increase from a negative to a positive number is a negative percentage. Section 6.6, Nonlinear Data Transformations. All nonlinear transformations start from the same central motivation to change the shape of the distribution. This is a key distinction from linear transformations, which do not change the shape of the distribution. This means that linear transformations have the same effect for any data value, whereas the effect of a nonlinear transformation depends on the data value. Different nonlinear transformations warp the data into different distribution shapes, and thus the appropriate nonlinear distribution depends on assumptions about the data and the desired distribution characteristics. For this reason, there are many nonlinear transformations. I will highlight 5 in this section. In all of the transformations I discuss here, the monotonic relationship across all points is preserved. This means that if x1 is less than x2, then x1 tilde is less than x2 tilde, where x are the raw data and x tilde are the transform data. Preserving a monotonic relationship helps interpret the results of statistical analyses such as t-tests and correlations and regression. An example of a non-monotonic transformation is the sine function. That is, x tilde equals the sine of x, where it is possible that x1 is less than x2, while x1 tilde is greater than x2 tilde. Section 6.6.1, Rank Transformation. The rank transform changes the data from numerical values with some meaningful scale, like inches or euros or happiness rating, into ordinal positions. As a simple example, consider the following data set X and its rank transform data X tilde. So here we have data set X is 1, 2, 3, some ridiculously large number, 9, 3, 4, 8, 7, 5, 3, 9, 4, 5, 2.01. And then below that is the rank transform data set X tilde, which is 1, 2, 4, 5, 3. The rank transform involves converting the numbers into their ordinal positions. This transformation works by sorting the data values and then taking the sorting indices to be the rank transform data. For example, in this data set X, the number 2.01 is the third highest number, so its corresponding rank is 3. Notice that 2.01 turned into 3, and that ridiculously large number, with 9, 3, 4, and so on, turned into 5. In other words, the numerical differences between successive numbers have no impact on their resulting ranks. All rank transform data points are unit distance from their closest neighbors. And that is a huge loss of information. Indeed, rank transform is a lossy transformation, meaning that the transformed data contain less information than the original data. And this, in turn, means that once you apply this transformation, you cannot go back to the original data. And one practical implication of this is that you should rank transform your data into a new variable instead of overwriting the original data. Now, the numbers in data x and x tilde have very different interpretations. The numerical values in x reflect some measurement of the universe. Well, okay, in this example, they're numbers that I made up, but in real data sets, these numbers are reflections of measurable things in the universe. But the numerical values in x tilde are indices that encode relative magnitude positions while removing all information about distance between numerical values. So in the example above, the numerical distance between 2.01 and 2 is 11 orders of magnitude smaller than the numerical distance between 3 and 934, that huge number, and yet their rank distances are both 1. For this reason, do not confuse the first two elements in x with the first two elements in x tilde. They may appear the same, 1 and 2, but they are very different. The 1 and 2 in x are data values, whereas the 1 and 2 in x tilde are indices. Let's see another example. Take a moment to rank transform the following dataset. Dataset x is 10, 2, 4, 5, 5. What to do with the two 5s? It makes sense to assign them to the same rank index. After all, two identical numbers cannot be sorted. So maybe we could set x tilde equals 4, 1, 2, 3, 3. However, this is not the correct result. For several reasons, the rank transform has two additional constraints. First, the maximum index should correspond to the set size, meaning that the highest rank in x tilde should be 5, because there are 5 elements in dataset x. Second, the sum of all the indices should equal the sum of the integers 1 through n. So in this example, 1 plus 2 plus 3 plus 4 plus 5 equals 15. The solution, therefore, is to use fractional ranking, whereby the tied numbers receive the average of the values had they been sortable. In other words, x tilde equals 5, 1, 2, 3.5, 3.5. Now, the highest rank equals the dataset size, and the sum over all ranks equals the sum of 1 to n. This transformation is called tied rank. Averaging ties is assumed, and so for convenience, people just call it rank transform instead of fractional rank transform or tied rank transform. The rank transform is used in many non-parametric inferential statistical analyses, including the Wilcoxon test, a non-parametric alternative to the t-test, and Spearman correlation, which is a non-parametric correlation. Section 6.6.2, Logarithm and Square Root Transformations. These are two distinct transformations, but they are similar enough that I group them into one section. Logarithm transformation. A logarithm transform, usually called a log transform, is simple. You just take the logarithm of the data. The natural log is usually used, but any other base has a comparable effect. The impact of the log transform is that large positive values are compressed and values between 0 and 1 become negative and stretched out. Thus, unusually large positive values have less impact, and highly non-normal distributions can become more normal. See Figure 6.7. Figure 6.7 shows an example of non-normally distributed data in panels A and C that become more normal after application of the log transform shown in panels B and D. So this figure is arranged in a 2x2 grid of panels. The top two panels show scatter plots of data before to the left and after to the right application of the logarithm transform. And the two panels on the bottom show the histogram of the raw data on the left in panel C and the histogram of the natural log of the data on the right in panel D. And what you see is that in the left column, the raw data is highly non-normally distributed data, looks like a power law distribution. And in the right column, we see that the data are not perfectly normal. It's a little bit skewed to the left, but the data are certainly much more normally distributed after the log transform compared to before the log transform. Back to the text. The data in this example are not perfectly Gaussian distributed after the log transform, but they are certainly closer to a Gaussian compared to the raw data. The log transform is used for power law distributed data and data where the variability is proportional to the data values, meaning that the variability increases as the data values increase. In Chapter 4, I call this phenomenon heteroskedasticity, and it violates assumptions of some statistical analyses, such as regression. The log transform is valid only for positive value data because the log of 0 is undefined and the log of a negative number is a complex number. So if you have negative value data and want to apply the log transform, you could first shift the data by adding a context. Square root. The square root transform is obtained simply by taking the square root of the raw data. So y equals the square root of x. The square root transform is valid for non-negative data, and the results will be non-negative. The result is similar to that of the log transform in that larger data values are compressed more than smaller values, but the shape of the resulting distribution is different from the log transform. You can see an example of the square root transform and a comparison between square root and log transforms in figure 6.8, and you will get to explore this difference more in exercise 2. Also similar to the log transform, the square root transform can reduce heteroskedasticity. This paragraph references figure 6.8, which shows that both the log and square root transforms can scale down large values, but they are not equivalent transformations. This figure has 3 panels, A, B, and C, organized in one row. In panel A, we see the impact of transformation on data values ranging from a little bit above 0 up to 10. So the y-axis shows the transform data. It ranges from a little bit below -2 up to around 3. So we see that the natural log and the square root both have a nonlinear bend in them, but the natural log has a sharper bend compared to the square root function. Panel B shows a data histogram of power law distributed data. So you see values close to 0 have a much higher count, and as the raw data value increases to the right of the x-axis, the count or the frequency of occurrences decreases sharply down to 0. In panel C, we see that the natural log transform of the data shown in panel B has a histogram that is kind of normal looking, but it's shifted a bit to the left, or it's skewed a bit to the left, whereas the square root of these data do not look Gaussian at all. It looks like just a kind of very steep drop from 0. Back to the text. Section 6.6.3, Fisher Z. The Fisher Z transform is used to warp a uniform distribution with bounds -1 + 1 into an approximately normal distribution. This is achieved by stretching out the numerical values as they approach -1 or +1. The formula for Fisher Z transform is shown in equation 6.17. This equation states that x sub z equals 1/2 times the natural log of the fraction 1 plus x in the numerator and 1 minus x in the denominator. This paragraph references figure 6.9, which shows an example of transforming random data from a uniform distribution into a normal distribution. There are 3 panels. On the left, we have a distribution of data that is drawn from a uniform distribution. So the histogram is basically flat between -1 and +1, notwithstanding some random noise. In panel B, we see the histogram of the data after applying the Fisher-Z transformation, and this distribution looks quite Gaussian. Panel C, we see the impact of the transformation. So the original data are shown on the x-axis with values ranging from -1 to +1, and the y-axis shows the transform data with values ranging from around -3 to +3. And the transformation is definitely nonlinear, so values close to -1 are stretched down, and values close to 1 are stretched up. It makes kind of an S shape, like an S spun around on its side or rotated on its side. Back to the text. How can you make sense of equation 6.17? First, notice the natural log function, which indicates a nonlinear transformation. Second, notice that the function is undefined for any values of x larger than 1 or less than -1, because such values would produce a negative fraction, which is undefined for the log function. Third, notice that the equation is undefined when x equals exactly -1 or +1. These values would produce a 0 in the denominator or a 0 in the numerator, which would lead to the log of 0. Together, this inspection indicates that this transformation is defined only for values of x in the open interval of -1 to +1. Now consider what happens for values of x close to 0. As x approaches 0, the fraction inside the log approaches 1. The log of 1 is 0. As x approaches +1, the numerator approaches 2, while the denominator approaches 0, which means that the fraction becomes large and positive. And finally, as x approaches -1, the numerator tends to 0, while the denominator grows up to +2. And this means that the fraction tends towards 0, which means its log will be negative. I hope that explanation makes sense. Whenever you see a confusing mathematical expression, you can begin to understand it by considering the boundaries and the function's behavior as the variable approaches those boundaries. Another good way to understand a confusing equation is to explore and visualize it using simulated data. Now, it turns out that equation 6.17 is the same equation as the inverse hyperbolic tangent function in trigonometry. Therefore, in practice, the Fisher-Z transform can be implemented using numpy.arctanh in Python or atanh in R. The Fisher-Z transform is used to make data more appropriate for statistical analyses that rely on normally distributed data. You'll see an application of this in Chapter 12 with correlation coefficients which are intrinsically bound to a range of -1 to +1. Section 6.6.4, transform any distribution to Gaussian. It turns out that any arbitrarily shaped distribution can be nonlinearly warped into a Gaussian distribution. Footnote: I thought of this transformation while writing my neural time series data book in 2012, published in 2014 by MIT Press. I don't imagine I'm the first one to think of this algorithm, but I haven't managed to find another name or source for this. Back to the text. There are 3 steps to this algorithm. Step 1, rank transform the data. Step 2, min-max scale the data to a range of -0.999 to +0.999. Step 3, Fisher-Z transform the min-max scale data. Remember that the Fisher-Z transform is invalid for data values of exactly -1 or +1. That's why we min-max scale the data to a range of 0.999 instead of to 1. You can see an example of this in figure 610. The transformed data have a Gaussian distribution, and the monotonic relationship across the data points is preserved. On the other hand, it is lossy and non-invertible because of the rank transform. This paragraph references figure 10, which shows that transformations can be strung together to convert any distribution shape into a Gaussian. So we have 3 panels. Panel A on the left shows the raw data histogram, which is a power law distributed characteristic. Panel B shows the histogram of the data after applying the transform that I just described, and it looks very Gaussian. And panel C shows a data comparison with the original data, so a scatter plot with the original data on the x-axis and the transformed data on the y-axis. In this case, it appears that there is some range of the original data where the transformation is roughly linear, and then values close to 0 have a strongly non-linear pull to them. Section 6.7, Interpreting Transformed Data. Many transformations change the units of the data. This is neither good nor bad, but it may require a change in interpretation. Z transformation is arguably the easiest to interpret and also facilitates interpretation of statistical models like regression. For example, regression parameters with z-scored data might be interpreted as, quote, each standard deviation increase in variable A leads to a 0.4 standard deviation increase in variable B, end quote. Other normalizations remove the scale of the data, but do not themselves have an easily interpretable metric. With min-max scaling, for example, the transformed data boundaries are fixed, but their means and variances are not. Regressions on min-max scaled data are best interpreted as changes in one variable associated with changes in another variable without defining the units of those changes. Nonlinear transforms present the greatest interpretational challenges. For example, imagine you log transformed your data and then performed a regression analysis. The regression analysis might indicate a linear effect of one variable on another, but that linear effect is actually based on a non-linearly transformation applied to the data. Thus, the effect is actually nonlinear. Now, this is not a flaw or even a severe limitation, but it is something to keep in mind, and it gets even more confusing if different variables are transformed in different ways. This paragraph references figure 611, which shows that nonlinear transforms can facilitate analyses, but can change the interpretation of the relationship. So in panel A, we have a nonlinear relationship between two variables that was linearized in panel B. Panel B shows that the relationship is linear between x and log y, but that means it's nonlinear. The relationship is nonlinear in the original non-transformed data. Back to the text. As I wrote above with min-max scaling, the easiest and safest, though not necessarily the most precise, interpretation of statistics on normalized or transformed data is that a change in one variable is associated with a change in another variable. Section 6.7.1, When to transform your data. In general, try to avoid transforming your data unless necessary. Most data are easiest to interpret and most meaningfully related back to the system from which they were measured in their original scale. Of course, data transformations can be effective and useful. They can improve interpretability in some cases, for example, z-scoring to compare variables in different scales. They can make data appropriate for parametric statistical analyses, for example, log transforming power law distributed data. And transformations are used in non-parametric analyses when assumptions of parametric analyses are violated. The point is that you should apply transformations to your data only when there is a specific reason to do so and not as a default data processing step applied without thought or justification. In conclusion, transform your data as little as possible, but as much as necessary. Section 6.8 is the exercises. As I've mentioned in previous chapters, I'm not going to read this section out loud because I discuss all of these in videos that I've created on my YouTube channel. End of chapter 6.